Okay. Can everyone hear me well?
Yep.
Yes.
Good. So last time I began to motivate this idea that evaluation is going to come in. We want to define addition for nats. So our nats are different from numbers once again. An example of a nats, as we've seen many times, is, for example, S of z. And we want to define addition on nats. And what this would mean is that our addition is going to be this construction called plus. And if I form plus n m for n and m metavariables for nats, then I want to say that this evaluates to something, and I want to define what its value is. This evaluates to, let's say, k, to say this evaluates to k. So for example, if I have plus s of z with s of z, what should this evaluate to?
S of z.
Good. Now, if I want to make this definition, I need to make a definition for every single possible nat n and every single possible nat m. And there are infinitely many choices. So I need to find some general rules that'll let me do this. And to this end, let's look at some examples. Well, what happens if you have plus, let's say, s of z with z? What happens there?
You just get s of z.
And can you think of any general pattern that this might exhibit, that this might be an instance of? Or more, go ahead.
It's kind of similar to adding variables, where like they have to be of the same base in order to add them.
Well, we are already from the outset, the universe in which we're working in is defining addition for nats. So in this discussion, it only makes sense to talk about adding nats and getting nats.
Yeah, I was just comparing the two. No.
Okay, I guess. But notice here, this nat is the same as this nat, right?
Yeah.
So what does that suggest? It might be generally true.
So
I can only have one z.
Is it that n plus 0 equals n?
Yes. So adding z to anything should give the thing itself. Or if we think about the world of numbers, n plus 0 is equal to n. So in the world of numbers, Now n is going to be a metavariable for a number. N plus 0 is equal to n, right? So in the world of knots, we define, because remember, what is our goal? Our goal is to say what the value of plus nm should be for all possible knots n and m. So we need to come up with some rules that are sensible. And we can come up with an instance of a rule that works for infinitely many knots. For all knots, n, we say that plus n with z evaluates to n. So n here again is a metavariable. This is a rule that applies when you take any n and you substitute a specific knot value for it. Then whichever expression you get on the left, it's going to be plus of a knot with a knot. And on the right, the value is also going to be a knot. So this defines an infinite family of rules. But there are still infinitely many cases to go, right? So where do we go from here? Any suggestions? Also, does this make sense to everyone, this definition here?
Makes sense.
Okay. Well, suggestions then for where to go next from here?
Instead of adding z, we can look at adding s of z.
Yeah, sure. Let's try that. So we can actually write down just directly what the general case of the rule is for s of z. By the way, looking back at the previous video, I frequently said s of z when I meant s of n or s of a knot. But in this case, I do actually mean s of z. So what should that be?
S of plus n with z.
Oh, but no, that's not a knot value. We want a value right now. Knots don't have pluses in them.
S of n.
Yes. So this rule right here is another honest to goodness rule where for an infinite family of values of n, if you add this specific knot value, you can plug in any knot for n, you can plug in any knot for n, and here you have an expression plus some knots, and that evaluates to some knots. And we can continue this process by giving another rule. So someone who hasn't spoken yet, say what this should be.
S of n.
Yep. Now, of course, we can't just continue like this. Each one of these is a separate rule, and we'd have infinitely many. Each one covers infinitely many cases, but there are still infinitely many cases to go. It covers all possible things that you can have for n, but for the second position, it only does each possible value of that argument at a time. And if we want to give a general statement, it's sort of hard to do in one step if we want to just talk about evaluation. Now, before, I gave examples like if we consider the statements plus z evaluates to z, this is slightly stronger. Or rather, in the world of numbers, 0 plus 0 is equal to 0 is a slightly rather 0 plus 0 evaluates to 0 is slightly stronger than saying 0 plus 0 is equal to 0, because of the discussion that we had before. You can say 0 plus 0 is equal to 0 plus 0. But this statement of evaluates to says that 0 is actually the value of this expression. If you were going to give an answer that was just going to be a single number that described this expression, then of all numbers, 0 is the one to choose. Whereas of all expressions that have some relation of equality to it, there are a lot of different things that you could write. So here, we sort of see, unless anyone has any suggestions for how we could do this with that arrow symbol, the evaluates to symbol, it looks like maybe we should talk about equality when making this definition instead of just directly talking about evaluation. So if something evaluates to something, we should say that it's equal to it. What is equality anyway? Well, it turns out that in logic, as we'll see at the end of the class, equality is one of the hardest notions to define. What does it mean to prove that something equals something? What does a proof of something equals something look like? And if you think about that, then you sort of need to understand everything else in logic to say what a proof of an equality looks like. Okay, that's a really high level statement, which we'll see at the end of the class, but equalities are hard. But also equalities satisfy some properties that we expect. So for example, when we look at is as opposed to evaluates to, and we use the word is in this sense, not in the sense of adjectives or belonging, then we should have that A plus A equals B implies B equals A. So equalities are things that you can reverse. Other things that equalities satisfy is that if you have A equals B and C equals B equals C, implies A equals C, and things like substituting equals for equals. Well, I guess not substituting, maybe replacing. Replacing A equals B. Replace if A equals B, then I can replace A with B. So what I've listed here are just some properties that equality should satisfy. I haven't defined what equality is, but if ever we use something that is equality, which we'll denote by an equal sign, then in the least, equality should satisfy these three properties. I haven't said anything concrete yet. But does anyone have any questions about that? Okay, more concretely, we had rules like plus n z evaluates to n. And whenever we have this evaluation symbol, we're going to say, well, if some expression has a certain value, then that expression is equal to that value. And now equality, unlike the evaluation idea, can be reversed. So from here, we can also get n equals plus Zn. And if we have a string of equalities, then we can chain those equalities. This is called transitivity of equality. So then, if we just look at the rules that we had above, we're going to have several families of rules. Let's write them like this. So first, we know that plus nz is equal to n, just replacing evaluation of equality. And again, equality hasn't been defined. I just said whatever equality means, it should satisfy these three properties, and we should be able to conclude equality from the evaluation relation. So looking at these, my goal is to generate some rule Right. What is our goal? I haven't stated our goal clearly enough. A knot is either Z or S of a knot. In the way that we wrote grammars. So instead of writing S of n for n a knot, I'm writing S of knot. Now, when defining plus, we have, I guess, the first rule that covers the case when, let's say, the second argument. Let's look at the structure of the second argument. If the second argument is a z, then we know that this is just n, or rather, more strongly, that it evaluates to n. What we'd really like is a second general form of this rule that works whenever the second argument is of the form S of a knot, so S of k. But now that I've written evaluation, it's sort of hard to say what this should be. Now, trying to find what that form is, I have a method for getting there that starts by looking at all of these families of rules that we have here and seeing if we can generate some common example from them, or if we have some pattern. So does anyone have any suggestions? Or put another way, let's look at rule A and rule B. How does one go from rule A to rule B?
You could probably say that in rule A and rule B, the second argument has a z inside the string. So I guess we say that we substitute the z for the n in the plus. Like, can you hear me?
Well, n is anything, right? So substituting n for z, that's not a statement that's I
Dead
like.
for n.
Right, but n is anything. N isn't necessarily z.
Okay, then, sorry, I should have been a bit more detailed. What I meant was you can define the plus operation by taking the second argument, emptying where the z is, and the evaluation of the plus operation would have you put the n in the empty slot where the z was.
Okay, so instead of z here, what we're putting is what? Down here.
Something like an empty space.
Okay, and what do we do with that empty space?
And then when you evaluate the plus, the evaluation has the n, has the first argument fill that empty space.
Oh, well, but okay, sure, we can do this. We can define a function that only takes a single argument, but then how do you define this function? You still have an infinite number of rules defining it.
But I said that you put the n in the empty space, right? So
Right. So that's assuming that plus is defined. If plus is defined, which it sort of is in an infinite number of ways, then this definition would give you a function that only has a single argument, takes a single number, and returns a number. Okay, this is called currying the function. Don't worry about that now. But still, that still leaves the problem. How do I define plus and empty space?
oh, I mean, sorry. What I meant was it's still plus nz, but the evaluation is like n empty space and put the n in the empty space.
Well, I shouldn't have this, right? I shouldn't have this. Anything, there shouldn't be two n's inside of a plus.
Oh no, I meant the entire expression evaluated to n.
I think what he's trying to say is that if you look at rule B,
Yes.
you see the second argument is s of z. So the value is, instead of s of z, the value is s of n. So that's what
Yeah.
he means by replacing
Oh.
z with an n.
Yeah.
I see. Oh. Okay, then for the third rule, what example would this be?
So
How would you do it in C?
the second argument you see is s of z.
Yep.
So the value is s of n.
Ah, yes. Okay. Well, okay, yes, that is the pattern that we see. But that pattern, you can describe it to me, but how do you describe it to a computer? Or put another way,
Don't you just substitute the previous answer into the new one?
so the previous answer, let's say, for example, if you were looking at rules B and C, right?
Yeah.
So
you-
I want to see how these two rules are related.
It's C is just S of B, whatever B is. What the previous
Yes.
one was.
So you've added this, and you've also added this, right?
Yeah.
So, okay, to the first people that were answering, I mean, okay, I think I understand what you're saying, but that's at a very high level is just you place all of the S's out front. But then you have how many number of S's are there, right? And then you have to count. And then you're essentially dealing with some other representation of numbers. Okay, that's unsatisfying, but I want something that's more elementary than involving any sort of counting. I just want to see what the relationship is between B and C. And the relationship is, well, we've tacked on an S in the, that's the thing that I want to highlight here is this. We've tacked on an S to the second argument on the outside, and we've tacked on an S to the answer. That's how you go from one rule to the other, right?
Yeah.
Now, if we have this, then we have this idea that we can substitute equals for equals. So if I take this and I substitute, we have that this here is the same as this here, right? So what happens if I replace that with a plus expression? What do I get?
You get S of plus n S of Z.
Right. Sorry if I'm artificially forcing us to get to this answer, but that is, well, that was my intention. So we see that, okay, you tacked on an S to the argument position, you also tacked on an S to the answer. But if you've tacked on an S to the answer, then the answer is S of the previous answer. Now you take the previous answer and you replace it with the previous problem. So here, if I put a dark red box around it, what I've done is I've substituted this problem in for this answer. Now, this only makes sense for equality. It doesn't make sense for evaluation yet, because this isn't a value. This has a plus inside of it. But let's see what we can do. Well, first off, what was special about, was there anything special about S of Z in this situation?
Well, S of Z, you can imagine you just tacking the S onto the Z, and with the new equality rule we just defined, that can be used to evaluate rather than find equality.
Oh, yes, but what about this S of Z? This S of Z, which I guess matches up with this S of Z. What if I just replace this S of Z with any possible, let's say K, a meta variable K? Then I have this rule, and I have whatever the answer is here. I don't know what the answer is, but I know that whatever the answer is, it's S tacked onto the answer of this previous case. And what is this previous case? What is the problem? Well, the problem has K, but without the outer S tacked onto it. So we had the idea that we tacked on an S both to the final answer and also to the question. So independently of what the final answer is, this final answer is S tacked onto this. So we can substitute the thing on the inside for the problem. Now, what is the problem? The problem is the same problem as we had before, except we no longer have that S enclosing the second position. So we get a general rule that for all knots k, again, this isn't a proof yet. We're not talking about formal proof. This is just an informal thing that says maybe this rule makes sense. Plus n of s of k for all knots n and k. This is equal to s of plus n and k. Does anyone not see how I got that? Informally. So what does this rule say then? This rule says that if we have any expression that has a plus, and the second position is of the form s of knots, then to equality, we can take this s and we can put it outside of the plus. So then, if we have something like plus, let's say, s of z with s of s of s of z, what happens if I remove the first plus? So someone just tell me what the symbols are. I move the first plus outside, the first s outside.
So it should be s of plus s of t,
Yep.
and parenthesis s of t.
Two s's, good.
Mhm.
Okay, someone else, the next s that I move out?
It should be s of plus s of z.
Yep. That closes the plus, and that closes the two s's. Then, okay, well, fine. Now this isn't as interesting. Then you remove the third one, and you get s of z, and then you get finally a z here. So then I have to close three pluses, three s's. And the final rule is, well, if you have plus z, then that just becomes the first arguments. Now notice that we got the answer here. So in fact, every single knot is constructed inductively. It's either z or s of a knot. And we're choosing the inductive interpretation. That means that a knot is anything that can be built up by applications of those rules. In other words, a knot is always some z with a bunch of s's in front of it. And this argument lets you move the s's out of the second position. So eventually you're going to get remove all of the s's, and you're going to end with plus something z. And that can just be replaced with whatever the first thing is. And so that gets you down to a knot. And notice that the first argument never changed in the course of this evaluation. It was always just s of z. So if we have this rule, which right now is stated as an equality rule, we see that if the rule becomes directed in the sense of whenever you have a plus and the second argument has an s, we remove it outside, then moving it outside will eventually get us down to a knot answer. So these equalities have a preferred direction. And in order to indicate that they have a preferred direction, I write arrows like this. Now, before I said that these arrows meant evaluates to in one step. I don't like that term. Evaluates to should actually be the final answer. So I will call this a one-step reduction. So these arrows mean reduces to in one step. Now, technically, if we looked at, okay, let's write down the rules that we have for reductions. So then we have two rules. Rule, I'm going to call this rule plus z. And this rule says that for all nats, well, I'm going to write this up top. Plus n z, that reduces to in one step n, right? So we had an equality before, but we can also replace that equality with a reduction. And for the second one, we couldn't evaluate it fully. I'm going to call this rule plus s. That says that plus n of s of k. I suppose this is for all nats n and k. That evaluates to s, that reduces to, in one step, s of plus n and k. Now, if we actually look at what's happening here, the first step, if we now justify it using these two rules, the first step is justified by applying, so here I'm going to write in blue the justification, by applying the rule plus s, right? Now, so the way that I write this is if I have something, I say, if these were equalities, I would say A equals B. And then following that, I'd write the reason that A equals B. So the reason this blue thing justifies this. Now, what's the justification for the next step?
The same thing.
Right, but is there a bit of a difference, though? Can anyone see a slight difference between the two?
The full expression is like s of plus of something and something, rather than
Right,
just plus of
so
something and something.
in other words, the rule is sort of being applied inside of an enclosing S, right? So for example, if this expression says you can do this or you can do this, well, the thing that we have isn't either one of these two things. It's S of the second case, but it's not literally the second case. Now, at the moment, we haven't talked about a language of expressions. At the moment, the only things in our language really are just nats, and everything else is just an auxiliary expression. So at later, actually immediately after this discussion, we're going to justify why it is that we can do the computation inside of an S. That is, we're going to give a third rule that says that you can do the computation under an S. But for the moment, let's just say that it's a convention that you can do computations under S's. So there is a convention going on that we say that if the reduction happens, if you ignore the outer S's, then the reduction also makes sense if you put a bunch of outer S's, right? And then the final rule would be an application of plus Z. And so that reduced you to your answer.
I have a question.
Yeah.
So in that same example, what if the first S you moved was the first S of Z, and then you would have S plus Z? Would that be fine?
So can you give me what's the problem is? It's plus what?
It's the plus S of Z, and then the next expression is S of Z, the one that you just wrote your notes on.
SSS, sorry, 3. So the what I had here?
Yes.
Okay. So, sorry, what now?
What if the first S you moved for like the next line in the reducing step was the S of Z, not the S of Z?
Ah, right. So the thing is that we aren't just arbitrarily moving an S. We're moving an S only because we have 2 rules that say you can. So we've settled on these 2 being rules. And we don't have a rule right now that says that you can move a first S out. Now, we could have developed this in a different way. We could have started by looking at not whether the second argument was of the form Z or S of a nat, but looking at the first argument. And then we But why don't we just have 4 rules? Why don't we also have rules that let you remove one of the S's from the first arguments? That's a question, right? I could actually give you 4 rules. I could do the same thing, and I could also say that you can move S's out of the first position. Can anyone see what a problem with that would be?
We may get into a loop. We may not get to our base case.
Oh, but you're still moving S's out. So there are only so many S's altogether inside of the plus across both arguments. So the question is, let's suppose that I introduce a third rule. I can also work out this rule in the same way that I did above. And let's say plus S prime. This rule says that plus S of K n reduces to S of plus NK, plus Kn. So now we have 3 rules. If I introduce this rule, what goes wrong? So let's just look at the line of the problem above, right? What should the second line be if we have both rules?
I don't know if this is a problem, but there are 2 different rules that you could apply.
Yes. So if we have this and there are 2 different rules that we're supposed to apply, we can apply, right? Remember what our goal is. Our goal is to define what it means for what value plus n and m have. So we haven't defined what value goes here yet, right? We've only defined some rules. Now, it's going to turn out that, well, in this case, every single plus expression is plus a nat and a nat. And if we look at the second nat, m, then that nat is either z or s of a nat, right? And if we have only these, the 2 rules in reds, that's plus z and plus s, then exactly one of the 2 rules will apply. Only one of the 2. And necessarily one will apply because every single nat is either z or s of a nats, right? Does everyone see that?
Yep.
Yeah.
Now, and I've argued that so you have a unique rule that applies, and that tells you what the unique second step is. And then you're back in the same situation, ignoring the outer S's, and then you have a unique rule. And I've also argued that, well, eventually, because knots are constructed inductively, you'll move all of the S's from the second position out, then you'll apply the rule plus Z, and then you'll get to a knot. So in other words, this process provides a unique step-by-step process that'll eventually stop when you get rid of the plus via the plus Z rule, and then you just have a knot value. And so then we can say that the value of the plus expression is that final answer. And this definition defines a unique value because there's only a unique rule that can apply. If we have two rules, then how do you know that both choices, or both exponentially many choices, if you continue going down, will give the same value at the end? But in this way, we can ensure that they'll have the same value at the end. And that's a very important thing in this discussion in order to define what the value of a plus expression is. So if we had a reduction rules where it was unclear which one we could apply, then it wouldn't be clear if this process defined a unique knot value. So your question as to why we don't have that rule, that is exactly the point. That is a very good question to ask. That's the main point. So I'll write that down. This is a very, very important point. If we had the rule plus, let's say plus S prime, which says that's plus S of K n reduces to, in one step, S of plus K and n, then there would not be a unique rule that applied in each situation. If we don't have this with only our two rules, each step is determined. Is fully determined. And I'll also say that it's fully determined by something. And what is it fully determined by?
The initial arguments?
Well, more specifically. I mean, the answer is yes, you're right, but more specifically. In other words, if I have an expression plus some knot and some knot, how do I know which one of the two rules applies?
You know which rule to apply, whether based on whether the second argument is a z or an s of something?
Yeah, so exactly. The structure of the second argument by the form so
I'm
looking
just a
back.
bit confused how plus what you just rule as the plus S prime rule, how is that different than the second rule? Because it just switches the order of n and k. So why does that
So
change anything?
the thing is that we could have defined a system with only the plus z rule and the plus s prime rule. So we
Oh,
could
instead.
replace it, but we can't have both. If we have both, then look at the first line here, right? The first line here has an s in the first argument and an s on the second argument. Now, if you can move either one outside, then you have to choose.
Oh, I see.
And it's the choosing that's really bad. Well, I haven't explained why it's really bad yet, but I've basically verbally done so. I
Okay.
mean, okay, I'll say it verbally again. Because the next definition that I'm about to make is, what is the value of this expression? The value of this expression is the unique number that you get to when you do this process until the plus is removed by the plus z rule.
Oh, so you need one to reduce all the way, and if you had a choice on both, you couldn't reduce it, right?
You wouldn't know which way to reduce it, and you wouldn't know that you'd get to a unique answer at the end. You wouldn't know that the final answer did not depend on the choice.
Oh, I see. Okay. That makes sense.
This is the most important point here, actually. So if anyone else doesn't understand that, I really do want to clarify it. Well, I'll write the conclusion down. And this is an informal argument. Informally, we see that repeatedly removing an s from the second argument eventually gets to a z, at which point the plus z rule applies. And we get nuts, and we get a value. So now here are the ways that I make these definitions. The first thing is I say, so this arrow meant reduces to in one step. So the first definition is write. Okay, I need to do these definitions following another discussion. But define plus nm goes to some value, let's say k, where k is the end results. Of this process. And we use that this process has a unique next step. And terminates. At an ats. So both of those properties were very crucial, and both of those properties were what enabled us to make this definition. So that defines plus. This is our definition of plus. Our goal in this section was to define plus, and here we've given the definition. Now that's informal because I haven't said what this process is. I can define more formally what the process is, and I'm about to do this. But what do people think of this discussion so far? Okay.
I'm
Oh, go ahead.
I'm following.
I see. So now I want to draw some pictures. So remember we had ASTs. Pictures for the rules. So now if I have a meta variable for a NAT, I'm going to think of the NAT as an AST. Well, for example, let's say S of Z. I visualize this as an AST from last time as S of Z. And so here I have a convention. If I have something like S of K, where K is NATs, then I will draw this as, well, in the way that you'd expect, S of K. Now, the thing to remember is, well, if K is a compound structure, then that K can't appear as a label here, because labels shouldn't have parentheses. So what K really is that K might be a subtree. It's may have, let's say K is identified with S of Z. So meta variables don't indicate nodes. Meta variables indicate other ASTs. All ASTs have a unique root, right? A single node that does not have a parent. And then if you want to just substitute a NAT for that meta variable in the AST world, what you do is you take that AST corresponding to whichever NAT it is, and then you just connect what would be K here to the roots of that tree. So in other words, all I'm saying is that our rules will look like this. The first rule says that if you have plus, now remember, ASTs correspond to S expressions. And if we just look at the Y, I had parentheses outside of the plus, right? Well, plus is also an S expression. Now plus is going to be an AST root label. If you're not completely clear about what this correspondence was, then don't worry. Look at this picture. This picture explains it. So our rules, we had two rules. The first rule was that, let me write them in a separate column here. So our first rule is the plus Z rule. And this rule says that plus N Z reduces to N. And in the AST world, well, can someone tell me what the AST for this looks like?
Would it be a plus sign at the top and then it branches off to an N and a Z?
Okay, yeah, exactly. And then this reduces to what?
N.
Yep. So this is the AST picture of the plus Z rule. So plus is just a label for a node in the AST, and then it has two children. What are its children? Its children are N and Z. And remember that N might be any NAT. So in particular, it's a substructure. So the child really isn't just the node, it's the actual subtree that's rooted at that node. Okay, and what about our other rule? Our other rule was plus S, and the plus S rule said that plus N with S of K reduced to S of plus NK. Okay, someone else, tell me the AST picture for this.
So the root would be plus.
Mhm.
And then one child would be n.
Mhm.
And the other would be sk.
And what does that look like? What does S of k look like?
It's an s at the top, and then its child is k.
Yep, exactly. And that reduces to?
S as the root.
Mhm.
And then plus as its child.
Yep.
And then n and k as its children.
Good, perfect. So really, we were discussing ASTs before, and though it may have sounded confusing, the point is that eventually we're going to be able to see everything in picture terms, right? So now we actually have pictures for what the rules look like. And we can actually look at pictures of the entire way that, so the full process going from a expression to an answer, that's called evaluation. And then each step of the evaluation is called a reduction. And all of the steps of the reduction are called the computational trace. Okay, I should have written that down above, but let's just look at what a computational trace is. So not looking at these rules for the moment, let's say we look at the expression plus S of Z with, let's be merciful and just do this. So this original input as an AST looks like, does anyone want to? Anyone?
Below the S is Z.
Mhm.
And then plus has another child, S. And it has two children, S and Z.
No.
Or
S's always have one child. S is
Ah.
S of something, right? And this is an S
Okay.
expression on its own.
Okay, so then under S is another S.
Yep.
And then a Z.
Yep. So in this situation, what is the first rule that applies? What first rule do we apply? The rules are plus S and plus Z. How do we tell which rule to apply?
S of k.
And you decided that based on?
The same as the example, you have to move out on the second term, move the S out.
So yes, the structure of the second arguments. Now, if we apply that rule, let's look at what it looks like in AST form. Well, if you have a tree where you have an S here, you can pull it past the plus, right? So here, what does that look like? So we're going to apply the rule plus S, and we're going to get another AST. So anyone?
So the root would be s,
Mm-hmm.
and then plus,
Mm-hmm.
and then one of its children would be s, and then z.
Yep.
And then the other child of plus would be the same thing.
Yep. So we can think of it as we've taken, so the color here isn't part of the AST, it's just an annotation on my part. We've taken this S and we've pulled it up here. Okay, I'll draw it here. Okay, and then for the next step, I'll just draw it. We pull the second S through. The first argument never changes. And then we get to our final step. So can anyone tell me what the final step is and what we get?
Well, you apply the plus Z rule,
Mm-hmm.
and you'd end up with S as the root, with followed by another S, and then one more S, and then Z.
Yep. So yes, and then the best, like if you just look at the ASTs, then you think of what does plus look like? Well, the input problem for plus is always some plus, and then you have two things hanging from it. And you look at the second arguments. Wait, yeah, the second arguments here. And you think of this as beads on a string. And then you're pulling it through the plus until eventually you get to a Z at the bottom here. And then just the plus and the Z, they collapse, and then these two attach to each other. So if you look at the order of the S's here, the order is preserved as you pull them through the plus. And so now we have a picture for this computation. It's a really cute picture, right? So don't fear ASTs. ASTs make things nicer. They make you have direct pictures for looking at computations. None of, and these pictures don't have parentheses, right? The parentheses are sort of an encoding of just the tree structure. And now looking at this and scrolling up above to this computation I think had one more S on the second arguments than we had here. And okay, so there's one more S, but ignoring that fact, it's basically the same thing. So that this thing right here with all of those parentheses, the picture for it is just those trees. Okay, I want to take I'm actually going to take 2 breaks this time. I definitely need to get to the end of the section of proofs. And before I begin proofs, I want to talk about one more way to formalize this. So right now, the only language that we have is the language of gnats. But I want to create a language of all of the expressions that appear in the course of this computation. And then we can define the reduction, the one-step reduction, as a reduction between expressions like this. And then we can define much more formally what it means to evaluate an expression. So the evaluation is the result of this process on expressions. Okay, so break until 2:47. No, 2:48. Resume at 2:48. I'm probably going to go to the end of time today because we need to get through proofs, but we're going to have 2 breaks in order to enable that. Okay, I'll be back soon. Any questions? Okay, so I'm going to resume. And the first thing that we're going to do is I would like to formalize this notion of doing the computation under the S. Before, when we applied each subsequent rule, well, I mean, let's just look at it in the AST form. We're applying this rule not to the root of the tree, but to some subtree contained inside of the tree. So this rule really applies under an S. And I want to specify what it means for rule to apply under an S. And that's going to be another rule. But in order to state that rule, we need to say what type of expressions are we even talking about? Because right now, the only syntactic category, well, the word syntactic category refers to a universe like NATS, which is restricted down from the bigger universe, like the universe of strings or S expressions or ASTs. We're working right now only in the universe of NATS, but we would like to work in a bigger universe that contains all forms of expressions that appeared in this type of calculation. So that brings up the question, what type of expressions appeared in this type of calculation? So a NAT is either a Z or S of a NAT. If you look at all of the expressions that you can see on the board right now, what are they?
Well, the last one is a nat, and the first
Yeah.
one is a plus.
Yes. Okay, yeah. So NATs are certainly expressions that we encounter. That's our final answer. And our starting point is plus. What is plus? Plus of, well, what does a plus look like?
It's plus of a nat with a nat.
Yes, good. So we have, just as a rough sketch right now, our universe has NATs and expressions of the form plus NATs, NATs. But what do we have in the middle?
Basically, S's of a plus,
Yes.
a nat and a nat.
S of the previous case. Now, what was the most compact way to write this grammar? It was beautiful, right? So in the grammar, I'm going to say that our universe consists of expressions. We're going to expand. Okay, I'm going to write it like this. Expands the universe of knots. The universe knots. To contain all the expressions encountered above. And as such, this universe is going to be called expression, EXPR. Now, what was one of the ways in which I defined the universe of knots that we spent a long time on yesterday? So what did we do yesterday? We talked a lot about ways that we can define nats as syntactic objects. And how did we define nats as syntactic objects? By way of what?
We said by inductive methods.
Oh, yes, but we can also encode those rules using... I didn't hear that.
Expressions?
Oh, I still did not hear that, but I think that was the right word.
We said expressions.
Oh, well, okay, how did we define S expressions?
We used grammars.
Yes. So I'm not sure if anyone said that, but yes, we would like to give a grammar for expressions now. So we're going to define what an expression is, and we're going to define an expression in terms of two top-level non-terminals. So an expression is either a nat, or it's going to be something called a combination, which is going to include either of the two other forms that we have. So we had the right answer before. What are all of the things that we encounter? We encounter either nats as our final answers, pluses as our starting answers, or S of pluses as our intermediate answers. Now, if we look at these two things, the last ones, have pluses in them. This is S. Well, actually, what I wrote is wrong, because it's not just one S. It's any number of S's. Of S's in front of this. But however we define that, it'll still have a plus somewhere inside. And whenever we have a plus, it's something that we can reduce. It's a reducible expression. It's something that's still not a value. It's something that we can do computation on. It's a combination of things. It's a compound expression. So that's why I call it a comb. Well, combination, as opposed to compound. So nats are going to be the final answers. Combinations are going to be anything that's still not a value, that still needs to be evaluated. And so then I would like to define, in turn, what is a comb? Well, actually, let's do the easy case first. What is a nats? So let's review. What is a nats?
Z or S of a nat.
Yep. So what I'm writing in green in my notes appears in italic letters. These are not actual symbols that appear in anything that's in our universe, but they refer to some subclass of objects in our universe. So our universe has nats and it has combinations. Now, what are nats? Nats are either Z or S of a nats. What is a combination? So let's see. Can anyone give me a definition? But if you are going to give me one, don't only if you haven't read the answer already in the notes. And remember that a combination is supposed to be either plus or some number of S's appended to a plus, right?
So would it be plus nat or S of
Yep.
a comb?
Oh, perfect. Yep. So yes. So we can either have S plus not nats, and then in the same way that a nat was either a nat or S of a nat, this plus is sort of the base case. It's the thing that bottoms out. And then if we just want to append S's in front of that, since that's already a comb, we just say it's S of a comb, which is either something that bottoms out at a plus, or else it's another S of a comb, but that eventually bottoms out at a plus. So I want to highlight the similarity for the grammatical definition of comb and the grammatical definition of nats. So this is a grammar for everything that we encounter in our universe. Our universe consists of expressions. Expressions are either nats or combs. Nats are either Z or S of a nats, and combs are either plus nat nats or S of a comb. So those words that I said, that's how you read a grammar. A grammar, by the way, does not, the equals are not equals like algebraic equations. It's just a notation. So for example, you have nat is Z or S of a nats. Z is a nat, but not every single nat is Z. But even if you reflected the fact that there's an or, the nats on the left-hand side and on the right-hand side means something different. And in a comb, the right-hand side has two nats appearing there. Both of those nats also mean something different. This is just a way to encode an inductive definition in the way that you had before. An expression is anything that you can prove to be an expression. How do you prove that something's an expression? You prove that it's an expression by either proving that it's a nat or proving that it's a comb. Well, we already discussed how to prove that something is a nat. You built it up from Z, the only thing that you know is a nat from the ground. And then you apply a bunch of S's in front of it with the second variance. For a comb, well, if you have two nats, you've shown that they're nats, you put a plus in front of it, you get that. Now, or you repeatedly apply S's in front of that, and then you get the general comb. So everything that we've encountered is an element of this universe defined by this grammar. Now notice we can't have nested pluses. We can't have plus and then we can't add another plus inside of it, because right now, pluses can only have nats, not combs. So we're not dealing with nested pluses. We're just working in this universe. Okay, and now here is where, why did I define this universe? Because now we have the nicest possible way to state what the rules of evaluation are. I'm going to write the rules of evaluation immediately after this. So our first rule of evaluation is, do I want to write it as, okay, I'm not going to write for alls. I'm just going to have the meta variable stay there. So we have the rule plus nz. In one step, it reduces to what?
N.
And what did I call this rule? What was the name of this rule?
Was it plus Z?
Yep. Then what was my next rule?
It's plus S rule. Right.
Plus what's the first thing? Go ahead. Anyone?
N of SK.
Yep. So these two rules really reflect what the structure of the second argument is. The second argument is always a NAT. Again, look at a combination. The only time that you can introduce a plus is if the second position has a NAT. Now, every single NAT is either Z or S of a NAT. These are two variants, and the two variants are mutually exclusive. Actually, this grammar also has mutually exclusive variants. A NAT and a comb are always different. These two variants for a NAT are always different. And if you look at a comb, they're also different. These don't have S's in front of them. These have S's in front of them. And you can always distinguish a comb from a NAT, even though both may have S's in front of them, in that a comb always has a plus. So a comb is always this reducible thing. Okay, so the NAT grammar also has, well, built into the mutual disjointness of these syntactic categories, or these variants, is the disjointness of the two rules for NATs. So it's either Z or it's S of K. And if it is S of K, then the rule that applies is, what do we get? What does this reduce to?
S of plus NK.
Yeah. And what did I call this rule?
The plus S.
Yeah. Now, in this universe, I'd also like to say what happens if we want to reduce an expression that has a bunch of S's appearing in front of it. So that rule will actually have a condition. It'll say, so if, let's say, S reduces to T, then, okay, I guess I gave away the answer. But so I want to encompass a rule saying that we can do reduction under an S. How do I state that rule?
You could say that if S reduces in one step to T, then you can substitute T for S.
Well, how would I write that conclusion?
Using the informal equal sign, S equals T.
Oh, I would like to write it as a reduction rule. So I would like to now define just the reduction rule. Also, this S is a lowercase s. It's by the way, what do I mean by what are S and T here? What types of things are they?
Expressions.
Yeah. So before we had N and K, what were N and K?
Nets.
Yes. Whereas S and T here are now expressions. So if S reduces to T, what do I want to say? I want to say that, well, this computation, where S reduces to T, can also happen inside of an enclosing capital S.
Then we want to say that S of S reduces in one step to S of T.
Yep. So this is a lowercase s reduces in one step to S of T, where now the, and this rule, so first off, this rule, does the word plus occur anywhere in it? Well, no, right? The word plus doesn't occur. So what is this rule really about? Is this a rule about plus, or is it a rule about something else?
It looks like you're building nets.
Sorry, say that again.
It looks like you are building nets. Because you're
Well,
adding S
combinations
upon a- yeah,
are built. Yes, combinations are supposed to look like gnats, right?
yeah.
There's a similarity between these two situations, but this rule. So let's look at what's the actual constructions that we have at the end. In the end, if we look at this grammar, we have a bunch of non-terminals, but the only terminals, in other words, apart from parentheses and spaces, the things that appear in our actual expressions are z's, s's, and plus, right? In other words, if we look at all of the ASTs that we drew, all of their nodes are labeled with S, plus, or Z. So of these three constructs, to which does the third rule apply, really? I mean, it applies to all expressions, but it talks about the nature of which one of these three.
Com?
Comb is non-terminal. I mean, of the terminals of these three things. Like, for example, these two rules here, they were rules about pluses. These were rules that say how plus behaves, right?
Mhm.
So if these first two rules say how plus behaves, what does the third rule say how what behaves?
I guess it's about how S behaves.
Yeah. So in general, when we have complicated constructions where we'll have languages and there will be a bunch of features, not just something like plus, and we'll have rules that direct computation to go under something. And those rules that direct it to go under something are really rules about the something, not whatever's inside. And such rules are called, wait, confluence? No, they are called congruence rules. And so this rule is called S-cong, where this is a congruence rule. And what do I mean by congruence rule? That it just directs computations.
Question, please.
Yep.
What is S and T, the small s, small t in the
Yes.
if?
Thank you. So here we had in the first two rules, n and k as metavariables for nuts, right? And here, this is we had while s lowercase s and lowercase t are metavariables for what type of syntactic category of these three?
It looks like you have two choices.
Oh, you could say that, but which is the most general? In other words, what does it make sense to say this rule about?
It has to have a plus in it.
Well, if you actually look at the hypothesis, S reduces to T, right? I haven't said this yet, but gnats you can't reduce nats because there isn't a plus. There's nothing to do, right? However, the hypothesis, if it's a nat, will never be met. But we can still say the rule if S and T are nats. It'll just never be satisfied. So what I'm going to say is that these are metavariables for expressions. Now, what happens if S and T are nats, not combs? Well, this rule has a condition. In order for this rule to apply, to actually say something meaningful, it's an implication. If something, then something. You can always say if something, then something, but the if might be false. And then in that situation, the rule isn't helpful, but the rule still makes sense. It just isn't helpful. Now, if you have S as a nat, then there is no T for which S reduces to T, because there's no further thing to reduce S by. Why? Because how is reduction defined? Reduction is defined by one of these two rules. So if S were going to reduce to anything, eventually the reduction would have to be a result of one of these two rules, which means that only things that have a plus in them somewhere inside them, maybe nested under several layers of S, are things which will have one of the initial two rules applied to them. So in other words, if S is a nat, then there is no T, but the rule still makes sense. So in general, we're going to say that S and T are metavariables for expressions. Now, on the other hand, if you looked at the first thing, right, it does not make sense to say that N and K are metavariables standing for expressions. Why? Because what is the meaning of a metavariable? The meaning of a metavariable is that if you take a specific thing, like S and T are expressions. Actually, yeah, I know how to explain this. This is really good. Thanks for asking. Here is the good explanation. S stands, lowercase s, for an expression. So an example of an expression is S of Z, right? That's an expression. Similarly, T stands for an expression. And we can say, for example, what is another expression? Another expression is plus ZZ. So as metavariables, a rule that involves metavariables says that whenever you choose actual values for those metavariables, well, you choose what the metavariables stand for, you can substitute them into if S of Z reduces in one step to plus ZZ, then S of Z reduces in one step to S of plus ZZ. This is a true statement. This is a rule. It makes sense. The problem is that its hypothesis is false, right? Now, on the other hand, when we had these rules above about plus and N and K had to be metavariables for nats. If N and K, you said they're any expression and you substituted an expression that had a plus, then that result would not make sense. It would be outside of this universe, right? You can't substitute a plus in for N when you have a plus and still remain in this universe. Whereas here, you can substitute any expression and still have a meaningful statement in the universe. Although sometimes it's a completely useless statement. This statement doesn't say anything useful, but it makes sense.
So you're saying this if-then clause is true. It doesn't matter whether the hypothesis and the conclusion are true, but the fact that one
Yes.
implies the other is true.
Yes. The hypothesis is false. Yes. So not only is this if-then clause true, but the if-then clause also makes sense. Whereas if for the plus statement, well, there isn't an if-then clause, it's just a plus. If you substituted an expression in here, then the results isn't in this universe if you have a plus. So this is, remember how we had this discussion of we're restricting ourselves to talking about only things in a meaningful universe. When I'm talking about in NATs, I have some abstract notion of what I mean by a NAT, and scribbles on a piece of paper probably don't qualify for that because I've just outruled it from the beginning. From the beginning, I say this is what I mean by NATs. I'm not even going to admit anything as to the question of whether it's a NAT or not. I'm saying that a NAT is something that has a structure in some universe. Well, in this discussion, the universe is expressions. And if you take something that has plus and you take this position where you'd have a NAT and you substitute another comb, then that's no longer in the universe. So that's why the metavariables here had to be NATs, whereas the metavariables here can be any expression. Or in other words, this was mentioned several times, NATs and combs both their grammars look a bit similar. If you take any expression in our universe, you can put an S in front of it, and it still makes sense as an expression. So that fact is precisely what ensures that it makes sense to put an S in front of everything, and that if we can substitute any expressions for S and T for those metavariables, then the resulting expressions will be in our universe. So these rules make sense for specific reasons. The first two rules make sense only because S of a NAT is a NAT, and because plus of any two NATs is an expression, and because S of a plus is an expression. The second rule only makes sense because if you take any expressions and you put S's in front of them, then they're still expressions. These rules are very, very carefully tied to the grammar. Okay, and here's the punchline. Here is the punchline. If you look at any expression, it is either a NAT or a comb, right? A NAT, no reduction rule can apply to it. It's like formally, the third rule, you can instantiate it with a lot of T's, but none of those T's will actually yield a true if clause that'll give you something that'll let you do it, take a step. Now, right. Now, every single other expression, it's a comb. Now, a comb is either a plus, not, and any single plus, not, exactly one of these two rules applies to it, because these two rules are characterize the two mutually exclusive variants of a NAT. And so we said NATs you can't do computation on. Combs you can do computation on. The two variants of a comb are mutually exclusive. For the first variant, exactly one of these two rules applies. And for the second variant, the third rule always applies. So in other words, no matter what expression you take, it's either a NATS or it has a unique one-step reduction. Okay, I think I've lost everyone there, but and I need to get to proofs, but let me just then write what this looks like. So, for example, now, if I want to make these justifications, let's say I look at S of, plus S of Z with S of Z. Then if I want to reduce this in the world of expressions, what is the unique rule that applies to this expression?
It will be the plus S rule.
Yes, and what was the results?
It will be S of Z.
No. Well, in one
Uh,
step. One step reduction.
one step. Okay. It's S plus S of Z. Let me see that again.
Oh, the rules? Here are the rules.
I think it should be S of plus SZ.
S of plus, well, first off, the first argument here, it doesn't change, right? So it should still be plus of Z. You have this, so the second rule is applying, you have this N here, it's still this N here.
S of, yeah.
What this rule looks like is you've taken this S and you moved it outside of the plus, right?
Yes.
So going back here, what does that look like?
It's S plus S of Z and Z.
Yep.
Yep.
And so the rule that I applied here was, what was the rule? What was the name of the rule?
It's a plus S rule.
Yep. Now, for the next reduction, which rule has to apply?
Is the S con.
Yes, the S-Cong rule. And so what happens is you first do the S-Cong rule. Now, once you do the S-Cong rule, you say, well, look at the expression on the inside, the S.
Yeah.
The expression on the inside, the S is this. And I ask, does any rule apply to the inside expression? So what rule applies to the inside expression?
It's the plus Z rule.
Yes, and what do I get?
That's S of Z.
Yes. And so the way that I'm going to write this justification is I'm going to write first S Kong in order to go within the first S, and then I write plus Z.
Okay.
So this modifies what we had before, now that we have the S-Kong rule. If you're working in several nested layers of S's, you have to write that many S-Kongs.
I see.
I'm going to do a more detailed example of this, but now, okay, so that's how this trace works. And now we can make this final formal definition that wraps everything up nicely in a bow. We say, so we have that any EXPR is either a NATS or a Kong. NATS do not reduce further. And to any Kong, a unique reduction rule applies. I wrote two rules justifying the second step here, but it's still at the top level, you're applying this rule. It's still at the top level, this is the rule that you apply. And then on the inside level, you do that. But at the top level, it's only a unique rule. A unique reduction rule applies. In other words,
Wait, when you write cong, do you mean comb or do you actually mean comb?
sorry, thank you. Comb, yes. Good. I need to erase this twice. Ah. There. So it was combination. It's also an M and not an N. Right. If C, let's say if S is a comb, or I'll use a metavariable C. If C is a comb, there is a unique Now, the reduction of a comb may be a NAT, right? So in general, if it bottoms out. So in general, there is a unique expression C so that C reduces to T. So we argued that to any comb, at least exactly one of the three rules applies. And then that gives an expression that it reduces to. That expression is unique. And there's always a step that you can take if you're at a comb. If you're at a NAT, then you can't take any further steps. Then we also argued, because all of the really essential steps of a reduction move an S outside of a plus, the process of repeatedly taking steps eventually reaches a NAT. Now I'm going to introduce a new notation. I'm going to say write S reduces to star T to mean S reduces in multiple steps, in 0 or more steps to T. So for example, if N is a NAT reduces in 0 or more steps to N, or anything reduces in 0 or more steps to itself, because you can take 0 steps. Then if if T is any expression, there is a unique NAT N so that T reduces in 0 or more steps to N. We define we then say that the value of T is that unique NAT. So this is how you formally, beautifully wrap the entire theory in a bow. This is all of the details of how plus is defined. We had to go through all of this, and now we have addition. We finally have addition for NATs. Many hours in, now we know what it means to add two NATs. There we go. That's addition. Any questions? Okay, so this is confusing, and I gave this in a much quicker pace. Also, I went to sleep late last night, so I'm a bit sleepy. Yesterday, I was more awake than today. It just means that I speak a bit more confusingly. My notes have a description of this, so I know that probably most of you did not follow that entirely, but read my notes. But also, getting to this statement of the rules was the most important part of this discussion. So we have 3 rules, right? And exactly one of these 3 rules applies. I now need to talk about writing proofs. I'm actually going to skip one thing first and then talk about writing and get to that later. I'm going to skip section 1.4 for a second so that I can start talking about proofs. And then I'll tell you what's in section 1.4. It's also it's very quick. But the key takeaway from this discussion that you need to know for this week's homework is that there are these 3 rules and that we are going to use these 3 rules in our proofs. And that the way that we use these 3 rules is like this. We write justifications after each step. And if we have to apply some number of S-congs, we write them first and then the rule that actually does the computation. These direct the computation. The plus S or Z actually does the computation. Okay, proof writing time. So we finally have addition. And I also should remark that this discussion that we had defining addition, we went through a lot of details, but I think that this discussion included about 50% of the important ideas in computer science. You have several weeks to understand what we did here, but this is how computations work. This motivates what computation is. In fact, this idea so whatever I've taught you, this thing formally in the literature, this is called operational semantics. And this is the way that we're going to specify how Racket as a programming language works. So there are going to be these one-step reductions. The one-step reductions are going to be defined by some collection of rules. Based on what the grammar is for expressions and based on the structure of rules, we're going to have that the grammar has mutually disjoint syntactic categories, so you can tell which one of these are, and the rules are going to be really based on what the categories in the grammar are, and they're going to be based around those so that at any expression that you have, precisely one of the rules that you have for your language applies for reducing in one step. Then we're going to have results saying that if you reduce over and over again, eventually you're going to get to some expression that you can't reduce any further. And either that expression is going to reveal that you wrote something incorrectly, or that expression is going to be a value. And that value is the value of the expression. So that is how a programming language in our model evaluates an expression. That was in a lot of details to get there, but this is basically all of the ideas that I need for the first half of the course. So next week, we're just going to go over this idea over and over again. Okay, proof writing time. And the only thing that we need to bring in from the previous discussion into here is the idea that we had those 3 rules. Any questions? Okay. Okay, get ready. Actually, let's take a 3-minute break, and then we're going to 4-minute break, and then we're going to dive into this. So resume in 3 minutes, 4 minutes. Okay, is everyone ready? Any questions first? Okay, so you will be required to write 2 proofs on the weekends, and the way that I recommend doing it is to very carefully look, like read 5 or 6 times what I've written in section 1.5 of the notes. I have created a notation for writing proofs that's incredibly rigid, and no one would ever write proofs like this. But I think that it's the best way to start writing proofs, and I expect you to follow my conventions. But it's very worthwhile to write proofs like this. So the first thing is that we have some statements. So for example, consider the statement that for all gnats, n plus n with s of s z. Now, for proofs, I'm going to make things easier. We're going to work with equalities, work only with equalities. In other words, don't consider the symbols. Use evaluation or one-step reduction. That comes later. So both of these should imply equality. If you have evaluation or if you have reduction, then you have equality. So I want to say that this is equal to plus S of n for all knots n. This is a statement. Now, this requires a proof because if we look at what our rules are, technically when we were investigating what our rules should be, we had this as one of the special cases. But in the end, we settled only on our definition of these three rules. And what's plus n with s of z is does not follow immediately from any one of these three rules. So we do need to prove it. Now, this is something that requires proof. So first off, how do you write the proofs of statements? Your proofs will be written in text documents. So I'm going to write a bar here just to indicate that this is what your proof looks like. The way that you write it is that you write claim, then you write the statement of the claim, then you, on a new line, you write proof, then you write the proof of claim, and then you end the proof with a QED. So this is the basic template for proving something. You state something and you prove it, and then you write QED. Now QED is quod erratum demonstratum. That which is to be demonstrated. Now, how is that in Latin? In Latin, that is, yeah, quod, Q-U-E-D, Q-U-O-D. That which was to be demonstrated. Meaning, I was supposed to prove something, and this says I have just proven it. So this is how you say I'm done. And as another convention, if in the course of your proof, you need to prove a subclaim, you want to state and prove a subclaim, you write, so this is inside of your proof. And I'll give you examples of both of these. And everything that I'm saying right now are just conventions that I'm enforcing for only your first two assignments. You write to prove. Then you state this, what you want to prove, statement of subclaim. Then you give the proof, but you indent with 4 spaces. And then you write, what did I write? So I want just be consistent. And I didn't have the chance to print this out. As required. So I don't have a QED outside of this. I only have a QED at the end of the outside proof. But on the inside, if I need to make a statement, then I make a statement like this. I say to prove what I'm about to prove in the middle of a proof. I indent, I write the proof of what I'm about to prove, and then I write as required. That establishes the statement of the subclaim. Okay, so right now I haven't said anything. Right now I've just said write things like this. Let's actually look at this statement then, and let's investigate what its proof would look like. So right now we're going to start informally. The statement is for all nats, plus, for all nats n, plus, let's say n with s of z is equal to s of n. So if n is any nats, so it's a meta variable, but we've actually imagined that it stands for a specific nats. What can you do? So can anyone tell me what I can do with this expression? So what's the next thing that I write?
S of plus n s of z, and that would use
Yes.
the plus s rule.
Good. So for these proofs, remember that we're only using equality symbols. So just don't worry about what symbol you use, just use an equality. But yes, and then you have to justify this, and the justification is that you use the plus s rule. And then what's the next thing? Someone else?
We will apply s-con and then plus s. That
Yep.
will be s of s plus nz.
And you applied, as you said, first s-cong, and then within that you applied plus s. And then finally, someone else?
Also, it's equal to s of
Oh,
n.
sorry. Yeah, s of n. Good. And what rules did I apply?
Oh, we apply 2 s-con rule and
Yep.
1 plus z rule.
Yep. And I write both s-congs. Oops. So you do this calculation, right? If n is any nats, if n is actually stands for any nats, you go for, oh, any questions?
Yes. Can you just restate how we applied to S-Con rules?
Right. So in the context of the previous discussion, which you don't have to understand that in order to see why this is the case, what type of expression is this in the universe of expressions? It's S of some expression, right? So the reduction rule that applies to S of anything has to be an S-Cong, which directs computation to the inside. Now you're asking, so let me go back to the, actually let me write what the statement of S-Cong is. The statement of S-Cong was that if S reduces to T in one step, then S of S reduces to S of T in one step. So here we want to know what the reduction of this expression is. Well, it is of the form S of something. So I look at the thing on the inside and I ask, well, okay, the thing on the inside, well, what reduction rule applies to it? Well, it's also S of something. So then I look at the thing doubly on the inside. And that's just this, plus nz. Now, when I have plus nz, the rule that applies to it is plus z, right? So that's the actual rule that does the computation, that actually changes something. And then the two enclosing s's on the outside, those correspond precisely to the other two applications. So if I can write it like this, or let's say, here is the first one, here is the second one. The outermost one is responsible for this, and the innermost S is responsible for this. Does that make sense?
Okay. Yes, thank you.
Okay. Now, let's just look at what this argument said. If n was any not, then this would happen, right? Now, what does that mean? Well, if we didn't have equalities, if we had one-step reductions, that would say that if you substituted the string, the S expression, the AST, of any not for n, then this would be a valid computational trace. It would be a valid sequence of steps. But the sequences of steps happen only for expressions, and expressions don't have variables in them. So this only makes sense when n is any not, and it makes sense for any nots. But nonetheless, what we want to prove is a for all statement for nots. So in other words, what we discover is that there should be some proof principle that says that if we can prove something for any knots, assuming nothing about the knots, then we've proven it for all knots. And the reason that we have such a principle is that, well, if you don't use anything about n, then you can just substitute any knot for n, and you get a valid proof. So we need some sort of machine that builds proofs for any n by substitution. And that machine is something that we have to accept as a valid strategy of proof. So that this statement proves the for all, it requires a principle. And that principle, I'm going to call a proof rule. And I'm going to call this proof rule the anonymous method. So this is something that we consider as a way that is an acceptable way to argue. But in order to accept it, we have to do so explicitly. Now, what does the anonymous method say? The anonymous method says we can prove a statement of the form for all n, for all nats n, some property that depends on n. I'm going to define this notation in a second. So this is any sort of claim that you can make that has n inside it. So here, for example, we have the statement that plus n s of z is the same as equals s of n. This is a claim that has n inside of it. And if we just want to, for every single n, we actually get a statement about nats that's meaningful about nats. Well, about expressions. And then when are two expressions equal? Well, they're equal when they have the same value, but that's auxiliary to the current theory. Equality behaves only as the rules dictate. Okay, sorry, that's a bit of a tangent. But I can label each of those statements for each n as p of n. This is just a label. So how do I prove for all nats n some statement involving n? I can prove a statement of this form by proving it what did I write? I want to be very consistent with what I wrote here. Okay, so I wrote it like this. By letting n stand for any nats, for any arbitrary nats, or for any possible. And proving p of n, where now we imagine that the meta variable n is meaningful. So this is a proof rule. It's something that we explicitly have to admit into our system. And this is one of the two ways which we'll discuss today on how to prove a for all statements by the anonymous method. So what this proof rule says precisely is, if you look at the proof above, that this proof proves a for all statements. Any questions?
But here you didn't use the format that you were describing earlier that we would need to use, right? It's not.
Oh, right. So I'm about to tell you how you'd write it. Right. Thank you. So how do you actually write it? To write, so to write this, an application of this methods, to prove a claim or subclaim, so in other words, I'm now going to tell you that if you want to prove some statements using the anonymous methods, where that statement is either a top level statement or a subclaim. So I'm going to tell you what to replace proof of claim or proof of subclaim with here, if you want to use the anonymous method. And what you do is, so suppose that you're trying to prove, you want to prove the statement for all n p of n, where p of n is some specific statements. Then what you write is, first, by the anonymous method, and you have to indicate what variable you're making anonymous. On n, then you have to indent it, and then you have to write let n be any nats. So now n is a meta variable standing for any nats, but the thing is that now in our formulas, we can actually apply rules as though n were some nats. Then you write some proof of the statement P of n. So now you need to prove this statement. Then once you've proved it, you go back to the level of indentation that you had at the top, and you can write hence for all n, for all nats n, P of n. So proof by the anonymous method introduces two levels of indentation. First, you say let n be any nats, and that's already one level of indentation. And then you have to prove the statement P of n. Next off, I want to say that if you want to do some calculation, if you want to chain equalities, or if you want to do anything with equalities, By the way, you don't have to memorize this. It's very carefully written in the notes for section 1.5. And I'm about to do an example that combines all of them. You write, we calculate, or what did I do? We compute. Oops. And then you write expression 1 equals to expression 2, and then you write your justifications here. And then you have as many copies of the equalities as you want. So you can continue this. Whoops. Okay, putting all of this together, let me show you a actual formal proof, the way that I expect you to write it on the assignments of the statements. So putting this all together. So actually, I'm going to scroll here, and I'm actually going to give you the proof. This is how I'd expect you to write this proof on your assignment if you were proving this. So we write claim on the next line for all nats n, comma, plus plus n s of z. Then on your computer, you'd actually be able to do this on a single line, but I'll go here. S of n. That's the claim. Then you write the proof. So first off, the proof is going to be by the anonymous method, right? So the first thing is we write is by the anonymous method. And you also write the variable which you're going to use, apply the method to. Then you write let n be any nats. Now, what would we like to do? We would like to prove something, right? we would like to prove n makes sense as a NAT. What we want to prove is that plus n s of z equals to s of n. How do we do this? Well, we compute. How do we compute? Well, we write plus n s of z, and then we do what we did before. We write the first step as s of plus n s of z, and then we write the justifications. This was by plus s. Okay, then you copy what you had above. For the sake of interest of time, I'm actually going to skip that, but I'm going to show it to you on a different screen in a second. Then you eventually get to s of n. And in order to do this, you did s cong and s cong again. And then plus z. So that completes this calculation. And then you had a to prove here. So at the end of the to prove, you write as required. So this as required matches this to prove. And then you had the anonymous method. Now at the end of the anonymous method, after you've established this claim under let n be any nats, you can go to the top level and you write hence for all nats and then you write what you've just proven, s of, plus n s of z equals to s of n. And then you write a QED. So that is a very verbose, very extended way to write this proof. But on the notes, you'll see that all of these elements, all of the rules about how to indent them, all of them are carefully written out. And it's just a template. So you think about this proof and you think, what did we do? Well, we have a for all statement. How do I want to prove a for all statement? I'm going to let n be any number, and I'm going to prove it for that number. Now that proof rule is the anonymous method. So my proof is by the anonymous method. So I begin my proof by saying I'm going to be using the anonymous method. Then the next line always, the anonymous method template requires you to write this line. And then you say, well, what am I proving here? Well, I'm going to say, I'm going to prove this statement. I write to prove the statement that I want to prove, and now makes sense as a NAT. That to prove statement is going to be end with an as required. Now, how do I prove this? Well, I actually do a computation with rules justifying it. So I write, we compute, I indent again, I go through all of the steps with all of the justifications. That does what I want. So I end my to prove with as required. And for any NAT, I've proven the statements. So that lets me, by the anonymous method, conclude that for all NATs, I have the statements. So let me show you this on from my notes. So in my notes, I remind you that this section. So the general template for establishing a claim is, actually, it's probably easier if I don't write this, but I highlight this on the screen instead, because this is what you're going to be looking at. And because I just wrote those. last night. So the general template for establishing a claim is claim, statement of claim, proof, proof of claim, QED. For subclaims, you state them, you prove them at indented level, and write as required. I remind you of what the rules are, and I give them names. If ever you want to introduce a name for the property of P of n in order to reduce the amount that you write, you can also write that. And then, looking at this proof of the anonymous method, this is what it looks like when it's typed up. It's actually much less intimidating than what I wrote on the piece of paper. So we have to understand this. This is a typical proof by the anonymous method. Does anyone have any questions?
Yeah, so why do we tab the to prove like beyond the let n be any nat? Like, what do we have to do?
Because n is some nat, right? Now you're working in a context in which the letter n makes sense. So
Okay.
now that you're actually working in that context, all of this is being done under the heading of let n be any nats.
Got it. Thank you.
So here I have the heading of I want to do a proof by the anonymous method. Then I actually go into the thing and I do the proof. Now, how is the proof done? I get let at n be any nats. Okay, now I need to work under the auspices of the place where the letter n makes sense. I've made sense of n as a nat. I don't know anything about it. It's anonymous, precisely why the method is called the anonymous method. But now it's actually a meta variable that stands for something meaningful. So now I can actually apply the rules of computation. Now, in here, I need to establish something. What do I need to establish? I say what I need to establish. I say, I'm going to prove this. Now, once I've established it, I'll write as required to close off the proof. How do I prove it? I compute. We compute. Then you go in the computation. Now you're doing a string of equalities. At each step, you write precisely what rules were used. Finish the computation as required. So for any nat n, we've proven this statement. So the anonymous method then lets us conclude that for all nats, I have the statements. QED. This is super formulaic. This is, no one would write a proof like this, but I think it is a good way to start writing proofs.
So how come you like restated the claim next to the to prove?
Oh, well, whenever I have a to prove, I am going to say what I'm going to prove. Now, why didn't I just say we compute? So I was wondering whether I should make you restate the claim again. I think it's a good teaching tool to have you restate what you're trying. For all nats, this is different from the claim that you're proving in here. Because this statement, it says my internet connection is stable. If there's anything breaks up, tell me. This statement is for all nats and this, right? This statement is different from this statement. This statement is plus n s of s of z is equal to s of s of n for some specific nats, which I know nothing about, but that's different statement than from for all nats.
Okay, I get it.
So just to emphasize that we're proving something that's very different from a for all. In order to prove a for all, right now, the only thing that I've told you about how to prove a for all is that you can do the anonymous method. I'm about to introduce a second way to prove for all statements, but you're going to have to use one of the two of the things that I introduce. This method lets you turn statements that have for all into statements that do not have for alls. And this, that you can do this, is an actual proof rule that we have to accept into our system. So for example, when we have proof systems on a computer, then the computer implementation of the anonymous method is that if you have a proof of a for all statement that uses the anonymous methods, and you have some nats, you can take that nat and you can transform your for all proof into a proof of the statement for a specific nat. And the way that the computer is going to do that is it's going to substitute n into each step, and then it's actually going to have a valid proof for that number. So the anonymous method actually has computational content where in order to specialize a proof of a for-all statement, it performs substitution. That's actual work. That's why the anonymous method is a separate proof technique that needs to be singled out. Okay, I know that I'm doing this a bit suboptimally, but okay, let's go back to the writing pad. Any more questions about that? So again, I strongly recommend that you reread section 5 several times. To see exactly how I do it. Your proofs should basically mirror the template of the proofs that I give you. Okay, so the anonymous methods is one way to prove for all statements. But it's not necessarily the most versatile. So let's look at the following claim. And right now we're going to work informally. So we're going to not write it in this verbose form. We're going to write it in the briefer form that we had above when working this out. And then I'm going to show you how to write it in verbose, fully indented form. Oops. Right. So consider the following statement. For all nats n, we have that plus z n is equal to n. So the statement that plus nz is equal to n follows directly from the rules, but this statement does not. So let's just try informally. We're going to write this informally. How would you prove this? So let's say you wanted to apply the anonymous method. What do you do?
First, let n be an arbitrary nat.
Sure. Now what? Well, n is either
N will be either Z or S of nat.
Yep. N is either Z or S of K for some nats. Okay, so right now we're proceeding informally. I haven't told you yet how to like formally have a formal thing for this. Okay, so what if n is z? If n is z, then what?
Then the expression will be plus ZZ, which evaluates, which is equal to Z by the plus Z rule.
Yep. Now, what if n is S of Z, S of K? Then what? Well, if we look at this, yeah, go ahead.
It will be plus z and sk, s of k. And we apply the plus s rule. That'll be s of plus zk, zk. Yeah.
That is plus s. And then what?
That looks like a circular argument.
Yep,
because-
we're right back at where we started. K, what is K? K is any arbitrary knot, right? K can be literally any knots.
Yeah.
So we're right back at the start. So in other words, the anonymous method doesn't work here. So it lets us shed one s away from k, but k may have arbitrarily many s's, and we want some finite argument on this page. So this right now doesn't work. So we need another proof method. If we just had the anonymous method to prove for alls, we wouldn't be able to prove this statement. So what should the proof method be? We need to discover another proof method. So this section now, it becomes interesting again. Everything that I did above about the anonymous method, that was just me telling you like rules about how to write proofs. There wasn't actually anything genuinely interesting or clever that was brought up, apart from the fact that the anonymous method is something that we actually have to accept as a rule into our proof system. We actually have to accept that that form of argument is a compelling form of arguments. Okay, going back to here. So the anonymous method doesn't do that because we do this and we get back to where we started. So what should we do? Well, we can start looking at a few cases and seeing if there is any patterns that emerge. So plus ZZ is Z, right? And that's because of some rule. I'm not going to write the justifications at the moment. What about plus Z, the next case, S of Z? In one step, what does this reduce to?
It will be s of plus zz.
And then what happens next?
That's s of z.
Yeah. Okay, let's do the next case. So here we have plus Z, S of Z. Okay, so, well, okay, what do we get?
This is the second argument, essentially. That will be plus the z and s of z.
Oh, so what you said is that what we get is this thing here matches up with this thing here. And I need another closing parenthesis. Oops. Right, and then what happens next? Well, the next step is look above. What we did above is that this becomes S of plus ZZ. And then that becomes S of S Z. And so if I'm going to highlight things, I'm going to put in a red box this and this. And if I look at where that goes, that is this and this. And then if I look at the justifications that I used here, whatever justifications that I use here, they would be the same justifications, but with an S Kong in front of them, right?
Yeah.
And similarly, if we look at like the first case, That also happens here. If I choose a different color, we have plus z. So something interesting is going on. And if we look at the next case, then what's going to happen? Well, there's going to be an extra s in front of here. It's going to go out front, and then we're going to have the previous case, right? So it was sort of a bit like how we worked out the rule for plus originally. So in other words, what we have is, well, we can prove that plus z is z. And then we can also prove, now assume that plus z k is equal to k for some not k. Switching to a more readable color. Then I claim that we can get a proof for the successor of k. So let's look at plus z and s of k. So in one step, write the one-step reduction.
That's s of plus zk.
And what rule did I use?
SCOM.
No.
Not really. It's S rule. Yeah.
Plus s.
Plus S.
Now, I have this assumption that plus zk is equal to k, right? So I'm going to give this assumption a name. Let's call this assumption int hype for reasons that will remain unknown for a few seconds. So then I can use this assumption. Now, remember that I'm working with equality, and equality has substituting equals for equals. And for this assignment, like if we looked at what happened here, whatever proof we had here, the new proof here had scong appended in front of it. That detail is something that's going to appear evident in the formal proof systems that we consider at the end of the class. But for the sake of the proofs that you're writing, we're just going to assume that equality makes sense, because equality is one of the hardest notions in logic. So I'm not going to make you deal with equalities formally here. So let's just suppose that we can substitute equals for equals. Then we have some hypothesis. The hypothesis says that plus z k is equal to k. So that's my hypothesis. And now I'm going to use that hypothesis to substitute equals for equals. So if I replace this with k, what do I get?
It will be just S of k.
Okay, and how should I write the justification?
In hype.
Yeah. So I just write the assumption. I give my assumption some name, and I state the assumption. So what I've shown here is that if I have a proof of k for some not k, I also get a proof for the not k plus 1. And I have a proof for z. And what are knots? Knots are constructed inductively. That means that I can count up to any number starting from 0. I can build any knot from z by applying s some number of times in front of it. And here I have a proof for the base case, z, and I have a proof that lets me put one s in front of it. So there should be a proof principle that lets these two pieces of information work as a proof for all knots. Right? Does that make sense that we should have a proof principle that can do that?
Yes.
Okay, and so this proof principle is called structural induction. Now, I'm going to state this principle for NATs, but as we'll see later in the course, this proof principle is really a proof principle about any inductive structures. So you have in math induction for numbers. Here you have inductions for any, an induction principle for any inductively constructed expressions. So in the next unit, we're going to have proof as structural induction on conditional expression trees. Or at the very end of the course, we are going to do induction on proofs. Proofs themselves are going to be tree-like data structures. And we're going to prove things about all proofs by structural induction on proof trees. So structural induction is something that's going to be a really, really, really powerful arguments tool. It's one of the most important concepts in CS. It's really a really good idea. Okay, so what is structural induction? So the proof rule says we can prove a statement of the form for all nats n, p of n. So it's the same statement that we had before. It's a for all statement for all nats n, p of n. Now, the anonymous method just said let n be any number and prove it. If you can prove it for any n anonymously, then you can prove it. But that didn't cut it for this proposition that we were looking at here. Here we had another proof method. This is another way to prove a for all statement. If we can prove, so we can prove that if we can prove first that, so the first thing that we need to prove is P of Z. And next that we can prove and now what should we prove? Can anyone guess what the statement should be?
We prove that P of K implies P of K plus 1, something like that.
What is K?
K is any net.
But right now in this discussion, we don't have K defined yet.
So we
So for
define it
example,
like for any net K.
So what is the statement then?
So it will be for any net K.
But for
P,
any is not a logical statement.
yeah, for all. That's for all.
Yes,
for
for
all
all.
net K.
That's P of what?
P of K implies P of K plus 1.
Yep. Well, P of S of K.
S of K, yeah.
I almost wrote a plus 1 as well. Okay. So first off, what is this implication? Actually, look at this. So okay. So what I've written here, that is the proof rule of structural induction. This is a really, really profound lesson. Like this is one of the main points. If you understand this, then you will have learned a lot. So what is the goal of structural induction? Structural induction is some proof rule that lets us prove a for all statement. Now, in order to prove that for all statement, we can prove it if we prove the following two statements. The first statement is P of Z, and the second statement is itself a for all statement. In fact, if we look at this for all statement looks more complicated. It involves an implication. But it's not actually a more complicated statement. What an implication means is that when we're trying to prove for all k p of s of k, we have a hypothesis at our disposal. It means that we get an access to an additional proof rule. And that proof rule really tells us that we know p of k. So though this statement may look more complicated, it's actually much more generous to prove this statement than it is to prove the other statement, because this statement gives us a freebie rule to use. And if we look at, for example, the proof that we had here, the process of going from p of k here to p of k plus 1, we actually invoked the hypothesis at some point, right? So structural induction gave us access to this hypothesis. And having access to the hypothesis is what made this possible. If we were just doing the anonymous method, we would not have access to this hypothesis and we'd be stuck. We'd get into a cyclic place where we return to our starting point again. But NATs are highly structured. They are highly structured. And so they let you return to your starting points. Only because NATs are highly structured can we actually return to our starting point. And now that we've returned to our starting points, that was exactly the assumption that we had in here. The cyclic structure of NATs and this rule for plus is what lets this hypothesis be useful. Okay, I need to tell you one more thing. So before I tell you how to write formally a proof rule for structural induction, I'll tell you how to prove an implication. To prove A implies B, well, you assume A and you prove B under that hypothesis. So you get access to another proof rule. So basically, a proof of A implies B is a proof of B, but at the beginning, you have to say that you're making another assumption. So how do you write this? Let me see what I wrote in here. I wrote, we assume. I wrote, suppose that. I wrote suppose that. Suppose that. A. And then I give a name to it. Name your assumption. Now, I do anything that proves proof of B. But in this proof, I can now use this assumption. Now, once I've succeeded in proving B, I need to exit my hypothesis. So I've shown that by assuming A, I can prove B. Then I need to conclude something from that. So then I make a conclusion. Hence, A implies B. And now I've returned to the original level of indentation. I'm closing the suppose clause. And I'm closing the suppose clause by doing something with this assumption and saying what it is that I've done with this assumption. So this is how you write a proof of an implication. Again, in the proof rules that I made up last night for how to write this. The indentation rules are completely arbitrary, but you have to do them for this assignment because it's a good place to start. Okay, so to write a proof by structural induction, well, actually, instead of writing here, and you watching me do this, I'll go back to here. And let's look at it. So here is how you write the general form of proofs by structural induction. For the anonymous method, we started off with by the anonymous method on n, right? For structural induction, you're going to start with by structural induction on n. Then, in general, structural induction is something that applies to any inductive type. Here, it's going to apply for NATs. And so I'm going to label the two ways that we can get NATs. And I'm going to write it as it is in a grammar. So I'm going to write here. So the first case is case Z. The second case is the case S of nats. So I want to prove a for all statement. I'm going to prove a for all statement for all nats by showing it first for all nats of the form Z, and then for all nats of the form S of a nats. But in this case, I can assume the results for the thing on the inside. So in this second case, I need to provide a proof of the for all statement. For all nats of K, P of K implies P of S of K. And how do you prove an implication? You write suppose the hypothesis, you name it, indent, prove, hence A implies B. Okay, so once you've succeeded in proving that in here, then you've proved the case Z and you've proved the case S of nats. Now you close off this block about bistructural induction on N by saying what you've concluded. Hence, for all nats N plus Zn equals N. So that's a nice way to indent the proof. And now, finally, for this proof, here it is. Here is the full way that you would write this proof, and as I would expect you to write something like this on your assignments. So both of your assignment questions, they're about twice, each one is about twice as long as this. However, this is a hint, this is a spoiler. When I did these assignments, I wrote a common lemma. Sometimes you might want to prove something not in the middle of your proof, but you might want to just prove a completely different proposition and use that proof. If you want to do that, then you just write another claim and another proof, and you'd call your claim something. My solution for each one is twice as long as this, but both of them have a claim, and the claim is the same. So in other words, the total amount of proofs that I had to write to solve both assignment questions was about 3 times as long as this. But you don't have to solve it like that. You don't have to search for a common unifying lemma. I'm actually curious to see what people will do. Okay, but, and again, you would do it by rereading this section many times and finding out how it works. Okay, so this proof. Claim, for all nats N plus Zn is N. Proof, by structural induction on N. Now, I'd like to refer to this proposition of plus Zn equals N with some name so that I don't write it over and over again. So I introduce a statement that just lets P of N denote, for any nat N, P of N denotes the statement plus Zn equals N. This is just something that lets me have much briefer notation. Now, I need to prove the case for Z. So what do I need to prove? I state, to prove P of Z. I've chosen to have you require writing to prove. Again, no one would actually write proofs like this, but state what you're going to do. Then, you want to prove this, it's going to end with an as required. Inside of it, at once in level of indentation, you're going to write the proof. What is the proof? Well, we compute. We compute, put it in indentation again. Starting point, ending point, assumptions that you use, justification for each step. That completes the case for Z. Next case, case S of a nats. Okay, so now you say, what am I going to prove? I'm going to prove for all nats K, P of K implies P of S of K. This is a for all statement. Now, this for all statement, we wanted to prove a for all statement. We have another for all statement. But this statement lets you have an assumption. But again, it's still a for all statement. How do you prove this for all statements? Now you use the anonymous method on K. And notice, you say what you're using the anonymous method on. Here, this was structural induction on N. Here, this is the anonymous method on K. Now, you let K be any nats. Now, what are you trying to prove? It's no longer a for all statement. Now it's just an implication. P of K implies P of S of K, where K is some specific nats. Okay, so I now want to prove an implication. How do I prove an implication? Well, I suppose the hypothesis, I give a name to the hypothesis, I indent, I give a proof, and then I write hence the conclusion. So, suppose that this plus zk equals k. Or I could have written suppose p of k. I give that a name. int hype. In other words, the inductive hypothesis. That's what it's short for. Now I say again, what am I going to prove? I'm no longer going to prove an implication. Now I'm just going to prove P of S of K. So I say, what am I going to prove? I'm going to prove plus Z S of K is equal to S of K. How do I do that? Well, we compute. The first step, I do plus S, and then I invoke the inductive hypothesis. So that finishes this computation. I said I was going to prove this. I've proven it as required. Now, this was a hypothesis. I suppose that. So what was the goal of this? I suppose this and I proved this. Hence, P of K implies P of S of K. Now, that's was the conclusion of this. That was nested inside of a to prove an implication. Have I proven that implication? Yes, I have, as required. So that closes that to prove. Now, this was let K be any NAT by the anonymous method. So now that I've let K be any NAT and I've proven this statement, by the anonymous method, I can conclude that for all NATs, K, P of K implies P of S of K. And that was exactly what I needed to prove for the case S NAT. So that completes this case. So that completes both cases inside of the proof by structural induction. Then I go back to the bottom and I say, hence for all NATs N plus Zn equals N QED. It is all beautifully indented, all beautifully structured. All of the elements of structure are described in this document. No one writes proofs like this, but this is the way to start writing proofs. Like, it is rigid. There's no room for writing English sentences that don't follow this form. It is just this super structured thing. Any questions? So you're not going to be required to write proofs like this beyond the first two assignments, in the sense that you're going to be allowed to do much more free-form things. It doesn't have to be indented in a specific way. You don't have to do these specific things. But here, you can think of writing this proof as sort of writing a program using a few types of programming elements. In fact, if we actually think about on a computer, what does the proof rule of structural induction do? Well, if our proof objects are actually objects in the proof system, then what is the computational content of structural induction? So structural induction is a proof of a for-all statement, right? And my proof system should let me take the proof of a for-all statement and specialize it to a specific number. Then, if I specialize in my proof system a proof by structural induction to a specific number, the computational content is not merely substitution as it was for the anonymous method. What it is instead is it is a recursive construction that builds up the specific proof term by building it up. You had a way to go from one to the other and you had starting points. So it actually does a recursive computation to build a proof term when you specialize. This is something that we're going to have in our proof systems at the end. This is why structural induction is something that you have to assume as a proof principle. There is substantial computational content behind it. So this highlights what we'll be doing at the very end of the course. Our goal at the end of the course is to take this statement, this proof, and put it on a computer. By the end of the semester, we will have a computer formally understand this proof. This proof, as structured as it looks, is not a formal proof. It is an informal proof. And we'll see how far we have to go to take this thing and transform it into a formal computer readable proof, which will be much shorter than this, by the way. It'll be a few, like 3 or 4 lines, but all of the elements in it will be super tricky to work out initially. We have to get to those concepts. Oh, can anyone tell me that they understood this, or I have no idea if anyone is following at this point?
I understand it at a
Getcha.
surface level. I just would have to run through it a few more times. to fully
Okay,
get it.
yes, understanding it at a surface level, I'm happy, very happy with that. Okay, so when are you going to understand it? When are you going to understand it? Well, you have homework due on Saturday and Sunday. So what I've told you right now is just some pointers on how to get started with the homework. For the homework, you're actually going to have to write 2 proofs. I wrote this guide in section 1.5 to be as helpful as possible. And now you have a puzzle. You have to figure out how to prove those 2 statements. Oh, any other questions? Okay, I need to say one more thing before I end today's meeting. The homework problem for the second day involves section 1.4. I'm going to go over it in the notes here, just very quickly. So if we looked at what the AST diagram was here for plus, imagine putting on one more apple in the second basket. Or rather, the first apple that you remove from the second basket is here sort of the last apple that you use to increment. Okay, that's vague, but we could think of another definition. Instead of moving an S outside, let's say that we move an S from the second argument to the first argument. So if we look at these 2 proof rules, they define a unique reduction. For it, it's still structurally recursive on the second argument. Well, it still uses the structure on the second argument. And in fact, if you look at these 2 proof rules, they never bring S's outside. So in the universe of discussing how these work, the universe doesn't even, it's a much simpler universe. That universe of expressions looks like this. I'm going to call this form of addition add. It's a different type of addition. So it actually looks like this form of addition is simpler, and it's much easier to make theoretically precise. You don't need the rule S-Cong. The universe is much simpler. And in fact, the first apple that you remove is the first apple that you add to the other basket. You just directly add it. If the first AST looked like pulling a string through add, this looks like a string draped over add, and you're pulling it on the left side, until the entire thing drapes over, and then you just get this. So it looks like this is a really much simpler definition. But it turns out that this definition is actually terrible for proving anything. Can anyone see why this definition would be terrible for proving things? So the definition is instead of moving an S outside, you move it from one factor to the other. So I'm going to give you a hint. Imagine that this S right here had a different color. Or rather, imagine that you took this computational trace and you put another S in front of this argument. Then what happens in one step? Okay, so let's just look at this example. After this S is out front, you can look at this problem. Adding S of Z to S of Z, right? So whatever computational trace that has, you can get that computational trace by just deleting the top S, right? So if you took your second argument and you modified it by putting in one more S, then the first step in the trace would just remove that, and then you recover the original trace enclosed in an S. Whereas here, if you put in another argument, then the rest of the computational trace is radically different. In other words, if you're trying to prove something by structural induction, what happens at every single subsequent stage in the computation is completely different and unrelated to what happens had you not put an extra s out front. So for example, if you try to prove that add is commutative, the simplest way to do that is to prove that add is equivalent to plus. Okay, everyone's tired and we've covered too much material, but I need to tell you that for the assignments, you can consider another definition of addition, add, which is different from plus. And the second homework problem requires you to prove that add is equal to plus. And you'll see that add is much more frustrating to work with than plus. Plus really is theoretically much nicer because you get to have arguments like this. And the reason that that is because the definition of plus is what is called structurally recursive. I'll define that next week. But for today, what's important to note is that for plus, you have 3 rules. And I have section 1.5 of the notes that describes a very, 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 very formal, rigid way to write proofs. And you're supposed to write a proof of commutativity of addition that basically looks like this. And you've all been added to the Marmoset system. So I'm going to have submission places open for that. And you've been added to Piazza, so you can discuss the content, but not the problems, not the homework problems on Piazza. And you can email me for help. But you have a legitimate puzzle to do those. Oh, go ahead.
Question, is the homework posted on Blackboard?
I'm going to post it on the course website, but I've also sent everyone an email with the statement of the 2 homework problems. I'm not going to post anything to Blackboard. These videos, the videos are automatically recorded and they're automatically stored to Blackboard. It takes a very long time to upload anything to YouTube. So if you want to watch this lecture right after the lecture, go to Blackboard. But otherwise, everything else is going to be via links that I send you on email or on the course website.
Did you also give us instructions as to how to submit the homework?
Yes, I will. So I've given you a link for how to log into the submission server. Right now, you don't see any places to submit the problems. I'll send you an email detailing it. I can also set up a stub problem 0 in which you can just practice submitting that's not worth credits just to make sure that it works so that close to the deadline, nothing goes wrong.
Okay,
I'll send you an email with instructions.
Thank you.
So today we did 2 very hard, very different things. The first thing is that I taught you basically what operational semantics is and how computation works. And this idea of a computational trace. We've suddenly got a definition of plus, and the definition of plus is computational. It's defined by rules. The rules are driven by syntax. Which rule applies purely is determined by the form of the arguments. And the arguments are defined inductively by ways on how to build them up from other arguments. And all of these brackets are there so that really you can interpret them as operations on ASTs. So there's a way to make pictures of it. And then there's the idea that the rules are done in a way such that at each stage, only at most 1 rule applies. And the things to which no rules applies are the values. So if you have anything in your universe, you just apply the rules over and over again. We've shown that this process has to terminate informally. We've shown this informally at some thing that can't be reduced, and that's a value. And then we say that expression has that value. So that's how we define evaluation. That's how we define plus. Add is defined similarly. By the way, the rules for add are going to be add Z and add S. I'll also write that in email. Okay, so that was the first thing that we did, but what's relevant to the homework is the statement of the 3 rules. Then, super relevant to the homework is how you write proofs. And I've given you all the templates here. Read this over and over again. Okay, good luck, and send me any questions and ask anything on Piazza, and don't give up on the homework. Most importantly, do not give up on the homework. Email me if you're super stuck. Work on it for a while, but do not give up. Sounds good? Okay. I'm looking forward to seeing your responses. Have fun.
Bye.